Hello world, welcome back to another episode of LeetCode Legends. My name is Brian, and this week I got a really great question for you guys. Matrix block sum, LC1314. Let's kick it off by reading the problem statement. Given an m by n matrix mat and an integer k, return a matrix answer where each answer ij is the sum of all elements mat rc, and it continues on here to give the valid ranges for R and C. But what it's basically defining is there's going to be a output element in the answer ij that correlates to an input region within the mat or the input matrix. All right, so let's take a look at it visually because it's much clearer once you draw out a few examples. So here is a sample input and a sample output on the right. So to compute the first element of the output, what we're going to do is look at a region of the input that is 2k plus 1 wide and 2k plus 1 high. So k is 1, and here we have like a 3x3 filter that's overlaid on the input that's being used to compute the output 14. 1 plus 2 plus 5 plus 6 is 14. And when we go to compute the next one, we're going to look at another region of the input that is the same, symmetrically the same, but it's going to be slid over by 1. So here 1 plus 2 plus 3 plus 5 plus 6 plus 7 is 24. I'm going to let the animation play out so you can get a feel for what's going on. Notice as the filter gets closer to the edge, the output gets smaller typically because we're summing fewer elements. Every time we make a summation, we're summing k by k bytes, basically. All right, so let's think about how we can approach this. This really looks like convolution to me. Convolution usually multiplies an input region by some filter weights and then accumulates the results in the output element. Here we're just adding them up. So like it's like convolution with the filter weights set to 1. So let's take a look at that approach. So convolution isn't that bad. It's just a lot of for loops. You iterate over every element ij, so like output ij, and try to calculate it. And to calculate it, you need another nested loop where you iterate over the region of interest in the input, which for us is like I minus k to I plus k and j minus k to j plus k. So it's like a square, right? That is 2k plus 1 by 2k plus 1 in dimensionality. And because our filter weight is 1, we're just adding up every element in the input block. Done. We found the solution. We just used something we already knew in convolution. If you don't know it, right, you can read up on it and practice it. It's just iterating through loops and stuff like that, right? So what's the time complexity of this? Because we have these 4 nested loops over m, n, and 2 of them over k, it's O of m by n by k squared. Is there anything wrong with that? It's not that bad because you really can't do better than O of m by n because you're computing m by n outputs. But k squared can be a problem if it's big. If the problem you're working with in real life only has k equals 2, 3, 5, 7, you don't really need to keep optimizing. But this is not the real world, right? We have a LeetCode problem to solve, and k is an input parameter to our function, and it could be anything. So question is, can we do better? Let's think about how we could do better. Could we use more space? The convolution approach was only using constant space. not counting the input, not counting the output. It was only using loop iterators, so constant space. Can we do some pre-computation on the input or pre-processing to make it easier to compute the final answer? Which leads us to dynamic programming, my least favorite concept of all. But I'm starting to get into it, right? So specifically, the specific case of dynamic programming that we're doing here today is called 2D prefix sum, but it's really just dynamic programming. So I'm going to approach this like it's normal dynamic programming. When we want to solve a question with dynamic programming, we want either a function or an array that holds or returns the answers to subproblems that we're going to later on combine to get the overall arching answer. So what we need to do is define that function or that array in this case. So there's a 2D array dp, and I want dp of ij to equal this mathematical equation. I'll let you think about what the mathematical equation is saying, but I'm going to just translate it into my way of thinking. What we're doing is summing the input array from 0, 0. So the upper left corner of some box is 0, 0. And the bottom right corner of that box is ij. And summing all the elements in that box. And doing that for every ij in this dp array. And this will be a lot easier to see as I walk you through what it looks like. So here we have the same input from earlier on in the presentation, and we have a sample dp intermediate. And so I've already solved, every solution, every subproblem is solved here. But I'm going to show you how these numbers came about. So to compute dp00, we're going to sum all the elements in the box defined by the upper left corner being 0, 0, and the lower right corner of that box being ij. So in this case, it's a box with only a single element in it, and it sums to 1. So next we're going to look at dp01, so the first column, 0th row, and to get this solution, we sum the box where it's bounded by the upper left corner of 0, 0, the lower right corner of 0, 1. So we're summing all the elements from 1 and 2. We get 3. Let's keep going. So basically, as we walk along this first row of the dp array, we're summing the first row of the input. All right, now we're going to go look at dp10. For this one, we're summing the elements within the box bounded by 0, 0 being the upper left corner and 0, 1 being the lower right corner. And just 1 plus 5 is 6. Now, again, summing the elements in the box bounded by 0, 0, and the lower right corner being 1, 1. And so 1 plus 2 plus 5 plus 6 is 14. And so this is going to carry on here. We're always summing the elements in the box shown on the left. As we get to the bottom left corner of the dp array, we're summing the entire first column, 1 plus 5 plus 9 plus 13. And finally, as it expands out to the lower right corner of the dp array, we're actually summing every element in the entire input. Okay. So now, the way I showed this here, computing this dp array would be very slow, like the way I walked through it, adding up all the elements in every box of the input. So it's not really helping us the way we're talking about it. It would be something like O of m squared by n squared. So we need a more efficient way to compute those prefix sums. And what we can do is come up with a recurrence relationship. We saw it was really easy to compute it for the first row and the first column, right? It was just adding up every element in the row. So that's O of n. And then adding up every element in the first column. That's O of m. That's quick, right? So what if we have that as a starting point, right? So I'm going to go, though, look at an arbitrary dpij. I'm going to look at dp22 here, right? So how did I get the number 54? We saw it before. I just added up all those elements in the box, but that's slow. How can I do it knowing that I already know previous subproblems? So how can I find the answer with some recurrence relationship? So what I could do is say I already know the answer to dp12 is 24. So I already know the solution for summing up these elements within the green box there. And I also already know dp of 2, 1. So the pink element, I already know that solution also. How could I compute this 54? How can I get to that number? So what if I added those two numbers up? So if I added 33 and 24, and you look at the pink and the green box on the left, it gets pretty close to 54, but there's a problem in that those two boxes overlap. So we'd be double counting 1, 2, 5, and 6. So what we can do to fix that is then subtract it once. So see, 1, 2, 5, and 6 cause a problem, but I can just subtract 14. So 33 plus 24 minus 14. Then there's only one more piece missing, and that's the current element that we're looking at. So we're looking at row index 2, column index 2 again, right? So 11. So we can compute 54 by doing 24 plus 33 minus 14 plus 11 equals 54. Cool. So I found a way to get dpij as a function of earlier solutions. And that's the solution. And instead of having to sum up all of the elements in the blue rectangle, I can, in constant time, just add up a bunch of these other numbers. Add and subtract, right? Okay, so now you might be wondering, how does this help, right? Like in the original question, we need to find the sum of an input region. The input region isn't always starting at 0, 0. So why am I doing all this mathematics where I'm summing regions of the input from 0, 0 to ij? Why pre-compute all this stuff to begin with? And so the reason is we can do more dynamic programming. If you haven't done enough dynamic programming already, we're doing a second round of it. Okay, so let's take a look at the input on the left and the output on the right. So we're trying to compute the output 99. So remember in the previous slide, we were looking at the DP matrix as the output, but now I'm looking at the actual problem output is 99. So 99 comes from the green rectangle, the green square on the left. So summing up 6, 7, 8, 10, 11, 12, 14, 15, 16. How can we get that sum from these prefix sums that we computed in our DP table? All right, so we can start off by looking at the prefix sum of the lower right corner of the input. So the lower right corner of the green box on the left side is 3, 3, right? Yeah. So input 3, 3 is 16. And when we take that index into the DP array, we get the number 136, which is actually the sum of the entire input, right? It's the blue box of the input on the input array shows that we're summing up the entire region. So we're going to start off by considering that amount and see how much does that overestimate the solution of the green box. So it overestimates it by the entire left column, the first column in the input. None of those numbers should be counted. So we could take 136 and subtract 28, which is the lower left corner of the DP table, one past the lower left corner of the input. So we're making progress, right? We started with 136, we subtract 28, and we're closer to the solution for the green box. But we're still over counting by 2, 3, and 4. So let's get rid of it. Okay. So 136 minus 28 minus 10. We almost have the solution for the sum of the green box. The only problem with the approach right now is we're subtracting 1 twice. So we have to add it back into the solution. 136 minus 28 minus 10 plus 1 equals 99. So we've come up with a way, it's like a dynamic programming approach to build the 2D prefix sum, or this DP array. And then from there, we can combine those subproblems to get the answer to the question. So this is going to be another recurrence relation. It's pretty long, but it's not really that bad. So output ij, is the sum of the lower right corner of the box in the DP table minus the lower left corner of the box in the DP table minus the upper right coordinate plus the upper left coordinate. So hopefully this was clear. You might have to walk through it a couple times to really ingest it, but it's pretty cool how you can do this pre-computation of the input and come up with block sums or sub-block sums of the input. So what did we do in taking this approach? We traded space for time. We started using O(n) squared space. So initially, like I said, the space complexity was constant O of 1, and the time complexity was O of m by n by k squared. After we took this dynamic programming approach, our space expanded to O of m by n, and the time complexity improved to O of m by n. So pretty cool, right? Trading space for time. And with this approach, we've achieved victory. The LeetCode gods will be happy. They will accept the solution, I promise. A LeetCode legend once said, "The code is in the description. Please remember to like and subscribe." I think it'll be more valuable for you to walk through the code on your own. Everything that I went over here is part of the solution. There's just a few corner cases you have to consider when the input region of interest is not full, like if you're on the edge case or on a boundary. So let's go over some key points for this question. So pre-processing your input can lead to significant speed ups. So if you ever implement something and you want to push it to the next level in terms of time complexity, you have to think about pre-processing the input, maybe using a little extra space. Also understand that prefix sums are a form of dynamic programming, and maybe just take a look at some questions that use prefix sums. I don't think they come up that often in interviews, but they're interesting. They're just a special case of dynamic programming. And remember that time and space are always trade-off components, right? You can trade time for space or space for time. If you're working in an embedded system, you might not want to be using a lot of space, and so you're okay with a slower algorithm. If you're on a supercomputer with, I don't know, a terabyte of RAM, then use some extra space and make it run faster, right? So always think about, is it worth it? With that, I'll be signing off this week. Thank you again for joining us on another episode of LeetCode Legends. Let me know in the comments if you enjoy this video, or if you want me to go over some other questions. I'm always looking for new interesting problems to go over, and would appreciate your feedback. So please like and subscribe also if you enjoy the channel. All right, take care.